I'd broaden the scope a little bit, and hopefully you find it interesting. So I'd like to start by thanking my collaborators. From left to right, Shangyu Cao, Christophe Karash, Romain Vasseur, and Joel Moore. And I'll also briefly be mentioning very recent work with Shangyu and Herbert Spohn. So the goal of a large research program over roughly a decade has been to extend standard statistical mechanics concepts to integrable and near-integrable many-body systems. The reason for this is that integrable systems are some of the only known solvable interacting many-body systems. And from the viewpoint of dynamics, they're interesting because they define an important universality class of non-ergodic systems. And in a sense, they are one-dimensional and non-generic compared to, say, MBL. But we care about them because they're physically interesting due to these exotic transport and thermalization properties. Theoretically tractable in the sense that both matrix product state numerics and thermodynamics are very well understood, and increasingly experimentally relevant in the age of cold atoms. And thanks to the efforts of many people here, the hydrodynamics of integrable systems is now well understood. And I'll be mainly talking about this in the context of Toda, where its physical meaning becomes extremely explicit. But a desirable long-term goal is understanding the large-scale dynamics of integrable systems. And I'm going to discuss some results in this direction, but obviously it's a very difficult problem for a general quantum system. Near integrability, there's really not a lot one can say at this point. Just a refresher of how transport works in ordinary many-body systems, for example, the transport theory of metals. One starts usually with microscopic time evolution described by kinetic theory. Zooming out, this becomes a set of hydrodynamic equations, one per microscopic conservation law. Usually these are dissipative, and through dissipation, they describe the transition to a long-time steady state, which is usually described by a Gibbs ensemble. And the real triumph of the last 10, 15 years has been extending all of these notions to integrable systems. So starting with Gibbs ensembles, replaced by generalized Gibbs ensembles some 10 years ago, hydrodynamics replaced by generalized hydrodynamics, and the Boltzmann equation replaced by what we call the Bethe-Boltzmann equation, just to give it a name. But the main novelty here is allowing for an extensive number of conservation laws. It's not rocket science, in a sense, going from the left to the right-hand side, but a surprising consequence of this integrable formalism is that there's no information loss in passing from kinetic theory to hydrodynamics. And this is very different from the normal type of transport where going to, once you integrate over quasi-momenta, you lose a lot of information. That's not the case here. Somehow, hydrodynamics is sensible to the full microscopic processes going on. Even in the, it's more that I know rho exactly, even with diffusive corrections. I can integrate, I can get moments, and I can go backwards in some sense. So I think it's true even with diffusion. If I have an evolution equation for rho, I can go back and forth between let's discuss. For Lieb-Liniger, it's plausible, maybe harder to justify for. Okay, so before describing GHD in detail, I just wanted to highlight some related work that I feel maybe has not been mentioned as much as it might be. Firstly, some very nice recent results on precisely this problem in 2D CFTs, where you start with a local equilibrated state, let it evolve in time, and get the finite time evolution in full detail. And for example, this predicts Schwartzian corrections, which I think are not present in GHD and might be an interesting thing to test. And in another vein, again, some years before GHD, there was this integrable hydrodynamics of integrable models in the context of Calogero-Sutherland. And I would also be curious to understand better the relation between these very elegant works and what's going on now. But it's worth saying that a very nice thing about GHD, the reason why it's kind of encompassing is it unifies these new results on quantum integrable systems with many scattered results on the literature and the dynamics of classical integrable systems. And this was noted by Benjamin in the very first paper, the formal similarity with hard rods, but I think it's true of maybe a far wider class of systems than you'd expect. So the basic equation of the theory without diffusive corrections, of course you all know by now it looks like this. And the first appearance was for classical hard rods, and the connection with GHD was developed in detail through this beautiful flea-gas analogy, which in fact, by modifying the solution of Perkus back from 69, inverting it in a way, you get this geometric interpretation of the time evolution discussed in the papers I mentioned. And I'd also like to comment that we followed up on the connection with the theory of classical solitons, in particular the Witten modulation theory of soliton lattices. And in that case, we showed that the hydrodynamics equations had an integrable structure that had been identified by Alan Kamchatnov in the context of their equation for KdV. So there are a lot of connections here that have been fruitful just for the back and forth between these new and old ideas. So why does it work for quantum systems? Well, three assumptions underpin the conventional semi-classical theory of transport in metals. You always assume infinite quasi-particle lifetimes. You assume that the effect of three-body scattering processes is negligible. You assume that your phenomenological mean field model for interactions is correct. And kind of the point is, for integral models, none of these are assumptions. Quasi-particles are stable, scattering factorizes, and the effect of interaction can be captured exactly by TBA. So just at a phenomenological level, it's going to work better than theories of transport that we're familiar with. And over 3 years, the theories passed many, many stringent tests, and the one I like the best is the cold atom experiment. But even so, its efficacy is somewhat mysterious. Firstly, how is a classical equation describing these strongly interacting quantum systems so well? So that's just somewhat mysterious to me still. And why does it appear to be valid near-integrability, as it was in the trap found in the experiment, as some theoretical work has indirectly confirmed, but it would be nice to quantify kind of the range of validity near-integrability in more detail. So as I said, that's more of a goal for the longer term. So now I'm going to talk about the Toda model specifically. So the Toda lattice is a well-studied toy model that's integrable both classically and quantum mechanically. The original motivation was the really paradigmatic non-thermalizing near-integrable system, the chain studied by Fermi, Pastor, Ulam, and Singu. And the Toda lattice captures some key physical aspects of this, but I mean, our main interest was just as a toy model. And it appealed to us for two reasons. The hydrodynamics of classical Toda was actually previously open, despite the long history of this model. And it's also perfect for understanding a little better what H bar is doing in this hydrodynamics between quantum and classical. So in February, 3 groups obtained the hydrodynamics of Toda simultaneously by different routes. Herbert Spohn making analogies with random matrix theory, Benjamin with a careful analysis of classical quasiparticles in the system, and then we working by taking a semi-classical limit of the quantum GHD in a controlled way. And we all agreed on the equation at the end, and I think that's maybe the most, and yeah. Yes. So I was told in my qualifying that Givontar has proved complete quantum integrability of Toda as well, if so I'm told. Usual GHD applies to the quantum Toda lattice, which is why it made sense for us to start quantum, although this isn't necessary. The ingredients are, as usual, the phase shift, here expressed in terms of a digamma function, the Yang-Yang equation, and this hydrodynamic equation for the Fermi factors. And if this formally, this is exactly the same structure as Lieb-Liniger. It's as simple as GHD gets, which is quite nice. The slightly tricky part is taking H bar goes to 0. And in many models, this can be somewhat subtle because you have to be careful with what the excitations are doing. In our case, there was a nice paper which derived the semi-classical limit carefully, and we were able to adapt that. You define classical analogs of your quantum quantities, and the first step is just to rewrite TBA exactly, but in terms of classical variables. And this is quite nice because these equations turn out to, it's just an exact rewriting, and it's also analytic in h bar as h bar goes to 0. So not only can you take the semi-classical limit, you can also discuss corrections. But first we'll do the semi-classical limit. And again, following these authors, you obtain the following formulae, which I think are in agreement with what Benjamin and Herbert obtained. And it remains to write down the Boltzmann equation for the semi-classical quasiparticles. For h bar is greater than 0, the density of states takes into account automatically both phonon and soliton type excitations. As h bar goes to 0, the paper we were working from concluded that solitons do not contribute, essentially because their effective mass goes to infinity, and so they can't contribute to the thermodynamics. So it was kind of a hypothesis that only the phonon dynamics would matter. This turned out later to be justified, and I'll explain why. But given the hypothesis that it's just phonons, you write down the phonon dispersion, get address velocity, and then in this case, GHD takes the form of a very familiar thing in condensed matter, which is a phonon-Boltzmann equation. So it's quite a concrete object, and it's just wanted to note that Alvise and collaborators also obtained hydrodynamics in a classical model, or showed it could be obtained by taking a semi-classical limit. Okay. So does it work? I mean, we derived it with somewhat hand-wavy assumption that a class of excitations didn't matter. And we compared with quite detailed numerical simulations of classical Toda with 2 reservoirs. And as we expect by now, it agrees very nicely. So this solves this standard non-equilibrium problem. So that's the classical theory. It works well. How about the quantum theory? Unfortunately, for the quantum Toda lattice, we still can't really verify hydrodynamics in any way unless these continuous matrix product state methods that we heard about this morning are taken somewhat further. It will be hard to test things like Luttinger and Toda directly, but we believe in its validity due to checks in models that we can simulate. So I think one of the most detailed checks that was carried out was finite time, finite temperature in XXZ, comparing with Christoph's TDMRG results. And for me, this is quite compelling evidence that at least the quasi-particle part of transport is captured exactly. There may be subtleties with the dressing, but the ballistic component of energy seems to be described very accurately. And other non-trivial numerical tests include the spin-Drude weights in XXZ. Again, this was a non-trivial problem the answer to which was debated for many decades, and then several people at once noticed that GHD actually solves this, and moreover, there's now been some analytical justification for why this is the case. So that's another quite non-trivial test in the quantum case. Also, wave function dynamics in Luttinger was tested, and I think the recent experiment can be regarded as a confirmation that this is working in a quantum Luttinger as well. So taking that as evidence, we can now consider the effect of varying Planck's constant in our Toda lattice. Say we believe hydro works for h bar not equals to 0, then it makes sense to just vary h bar in the equations I had earlier. And you can see from this that the main physical effect of varying it is maybe not very interesting. You increase Planck's constant and the density just depletes. There's an associated depletion of energy. But what was maybe more interesting in this case is the analytical structure of the leading order corrections. So just the quantum Fermi factor automatically comes with OH bar corrections, as you'd expect. These are less exciting. The main subtlety we found when we thought these were the only corrections for a while, and then we tried to compare with TBA, and actually the phase shift also leads to leading order corrections in a surprising way. So in a sense, the semi-classical limit is some kind of asymptotic limit. You're keeping your momentum constant, taking h bar goes to 0. These are large wave number asymptotics. So it makes sense to look at the asymptotics of the digamma function to get the phase shift. You have this prediction. Unfortunately, this can't possibly be physical because the asymptotic kernels you get this way are divergent at all orders. So we were a bit stumped for a bit, but it turns out that the correct thing to do is take a different kind of expansion. If anyone is familiar with this type of, we hadn't seen it before, but we'd be very grateful if this is standard in some context. But you can get it by successive integrations by parts, and very counterintuitively, it leads to a correction that's linear in h, despite the h bar, despite the fact that the phase shift is an even function, and you'd expect everything to be quadratic. So there are order h bar corrections to hydrodynamics, both from the phase shifts and the Fermi factors, and you can confirm it numerically, as in the inset of our earlier plot. So that's all I want to say about quantum corrections. And finally, one of the real surprises which came out of looking at Toda, which again Herbert and Benjamin were also very aware of, is this connection with integrability through the structure of the Lax matrix. So perhaps the clearest way to see integrability of Toda is through this Lax pair, these two matrices, in terms of which the equations of motion are just this isospectral flow. You have n conserved eigenvectors and eigenvalues, and that's giving you your integrability. It's clear that specifying a state, in this case, is equivalent to specifying spectral data of L. So a natural thing to consider is maybe you can turn this on its head in the sense that all thermodynamic properties of the model must then be reflected by the spectral properties of the Lax matrix, viewed as a random matrix but averaged over the GGE ensemble. In particular, we expect that the phonon density of states we computed, if it's really a physical thing, should just recover the spectral density of states of the Lax matrix. And the strategy was then to check completeness of TBA, of this semi-classical TBA directly, by randomly sampling the Lax matrix in this thermal ensemble. So this is a classical model. You define the canonical ensemble in the usual way. You have this randomness, which gives you a random Lax matrix, and you can maybe interpret TBA in that way. And we found that it worked. There were 4 decades of agreement. It worked very well. And so we deduced that actually this semi-classical procedure, throwing away solitons, was justified in the sense that the thing we get out at the end is precisely the spectral distribution function of the Lax matrix. And I should say that this, that you can go a step further, as Herbert did, and use this to get TBA directly from random matrix theory. So that's the very surprising result, in a sense, that TBA just becomes a theorem on random matrices. And Benjamin also pointed out this connection in his work. But using this interpretation, if you go back to the Lax matrix at large separations, you see it basically becomes a diagonal matrix in momenta. So this is maybe another way to see why this correspondence would hold. So what about currents? It would be nice to say something about them too, since they're the basic object in GHD. So the educated guess is just to take this density of states, the velocity, and say, well, this is the current. We know this in many models. But now that we have this connection with random matrices, it would be nice to relate it to the Lax pair somehow, or directly test this equation, equation 11, in some way. And it turns out to be possible. And the basic idea, which there are other ways to derive this, but this was how we got there, was to identify semi-classical quasi-particles with eigenvectors of the Lax matrix. So intuition, at large separations, the Lax matrix is a semi-classical limit of the translation operator. From the philosophy of asymptotic beta ansatz, we expect that eigenvectors should then be the semi-classical limit of beta quasi-particles. This is just, large spacings. The wave function has its product form. You expect there to be some correspondence. And the equation of motion for the lax matrix implies an evolution equation for states. The analogy is exactly the same as Heisenberg versus Schrödinger. And if you interpret this eigenvector as a quasi-particle, you can conjecture its velocity is just the average of this position. And so we played the same game as for the density of states, comparing our TBA guess with the lax prediction on the previous slide. And we found perfect agreement, which suggests that this formula is totally correct, and moreover, it's a statement about the eigenvectors of a random matrix in this particular model with this simple structure. And so a paper which came out today, I think, formulated this conjecture more carefully and tested it more carefully than we did in the first Toda paper. And then another thing that falls out of this, it gives you a kind of intuitive picture, shouldn't be taken too seriously, but of where the quasi-particles in hydrodynamics are coming from. They're eigenvectors of this random matrix L with disordered off-diagonal elements. So you can think of them as quasi-particles as being Anderson localized to sites by thermal fluctuations in the hopping matrix. And this breaks down in extreme regimes. One thing we showed in the very recent paper was that GHD can be derived complete without no quasi-particle picture, just by relating a conjecture on Dyson-Brownian motion to something on random matrix theory. And that is a way in which you can express this relationship between currents. So that's all I want to say about Toda. And now I'll move on to some completely unrelated work about hydrodynamics of near-integrable systems. In the context of quasi-one-dimensional Bose gases, hydrodynamics can be used to yield predictions for, say, free expansion or colliding clouds in the absence of a trap. And I've shown a figure we made, but obviously there are other figures that you've seen. And this has now been experimentally tested, remarkably. But the theoretical application to the physically important case of trapping potentials is still somewhat unclear. The trap breaks integrability. And one could add a force term as for the usual Boltzmann equation, but this is difficult to justify when K is not defined. And you might disagree over how difficult it is to justify, but the minimal question from an experimental viewpoint is, at what time scale does this break down? So that's what we try to explore in a, question? This is what we try to explore in a classical integrable system. So we chose the classical hard rod gas, which you heard about yesterday from Benjamin. It's really the interval dynamics in 1D, and it's easy to simulate numerically. The hydrodynamics without a trap was derived a while ago and has the standard form with a constant phase shift. And the question we looked at was how well does a minimal modification modify dynamics in an integrability breaking trap? Well, the naive expectation might be that the hydrodynamic equation is valid at short times before dissipative thermalization to a conventional Gibbs state. And this is kind of what we were expecting, but in fact, there were three regimes which turned out to be present. An initial regime of entropy-conserving hydrodynamics. It was accurate up till a characteristic time to chaos, scaling in this way with the parameters of the harmonic trapping problem. This was followed by a chaotic regime in which entropy increased. In fact, this chaotic regime was, for not too large systems, was quite well described by this diffusion formula of Bulchandani and others from the 80s. And then there was this late time regime where entropy saturated and the system attained a non-thermal steady state. Okay, so these were the three regimes we found. Going to start by describing the... yes, so it's... actually, it will be on the next slide. So maybe I'll show and then... Okay, so the initial regime here we simulated a Gaussian in a harmonic trap, and you can see some damping due to many-body dephasing, these hard-rod interactions, but it's captured very well by hydrodynamics up to this time scale. But after this, what we call T star, hydrodynamics breaks down and the evolution becomes chaotic. Interestingly, the chaos is not serious in a sense that it decays with the system size. So the Lyapunov exponent scale, as this was a fit, but 1 over n to the 1/4. And you can think of this as a justification for the Thomas Fermi approximation, dynamically speaking, that you can, the local density approximation works in the thermodynamic limit. How it does this is somewhat mysterious, but this is what we are confirming. But the really interesting thing is, where does this time scale to chaos come from? And our interpretation of it was that it occurs when the complexity of the real system, set by its size n, cannot capture the complexity of hydrodynamics, which is essentially the n equals infinity limit. So what you have in this plot is the phase space distribution function of an initial Gaussian in a trap for a small and a large number of particles. And for a small number of particles, you see that the spiral structure is just being lost on the accessible timescale, whereas for a large number, the size of the system is capable of reproducing these non-trivial spiral features. So the onset of chaos is delayed because the system has better reproducing power in a way. So we call this thermalization by complexity crisis, and it explains why, it helps to explain why chaos is suppressed as n goes to infinity. It's because the system can reproduce hydrodynamics better in a way. So after they, so this is a classical simulation. I think taking two initial states that are close together and looking at how the separation scales with system size. Shang Yu did this calculation, so if he's here, perhaps he could T star scales with n indirectly through these, through the density basically. So you can't access it directly. Okay, so then after the chaotic regime, the late time ensemble is non-thermal and solves the stationary hydrodynamic equation. So this was also quite surprising, that hydrodynamics works, it breaks down chaos, and then suddenly the late time ensemble is stationary and non-thermal and described by a stationary hydrodynamic equation. And in fact, this possibility was noted in the work of Doyon and Yoshimura on a note on generalized hydrodynamics. They explicitly drew attention to this possibility. So we verified it, at least in the hard rod case. So that concludes my classical discussion. We now, trying to generalize to the quantum case, we expect that some of these conclusions should hold in a quantum regime of small de Broglie wavelength. So I expect these are very specific to a trap. Yeah. Exactly. So the next thing I'll talk about is where you break with interactions and get a totally different kind of hydro, but yeah. Yeah. I think that's the end. So these timescales, we were at least 2 decades longer than the quantum pre-thermalization work, and we're pretty sure it just goes on forever because it's described by GHD in that limit, and there's no reason it should relax further. There should be fluctuations, but I don't think corrections in a sense. Okay, sure. But at the Euler scale, yes, Euler scale infinite time, we expect this to be. We didn't see it, so that's all I can say. 10 to the 4 was our maximum time scale roughly, and we didn't see it. Okay. So yeah, so for a trapped Lieb-Luttinger gas in the classical regime, it seems reasonable to expect that some of these conclusions carry over, that hydrodynamics will be accurate at both short and long times relative to T star. The onset of chaos will be suppressed as the number of particles goes to infinity, and the characteristic time to chaos will scale with physical parameters in this way. But of course, this might be hard to see because there are so many other loss effects in quasi-one-dimensional systems, experimental realizations. But at any rate, it suggests that the quantum Newton's cradle phenomenology corresponds to a short-time hydrodynamic regime, which I think is a generally agreed upon claim, but it's quite hard to justify in a lot of detail. So one thing we were doing was studying the quantum few-body problem for the trapped Lieb-Luttinger gas. So this is work in progress with Sheng Yu. There are strong indications of non-ergodicity, but it's quite hard to extrapolate to the many-body problem. So now for something slightly different, not really connected to integrability so much at all, perturbed Luttinger liquids. So generically, integrability is actually broken by interactions rather than traps. And some nice recent results on how this happens is a paper by Lammercraft interpreting this as diffraction in the three-body problem, and not this well-known pre-thermalization paper by Bertini and collaborators. But as far as I know, these are some of the few results so far. A physically important example is an ideal 1D metal, which, if it were ideal, would have divergent transport coefficients for charge and heat, but interactions or disorder are what actually give you the finite conductivities that you see physically. So the unperturbed Hamiltonian is a free boson Hamiltonian, but a nice paper showed that for irrelevant vertex operator perturbations, you can actually get the charge conductivity, its temperature dependence, from a field theory calculation using the Dyson series. And this was later tested numerically. So one realization of a Luttinger liquid is XXZ in a staggered field. You can verify that the staggering breaks integrability by looking at level statistics. For very small h in a large system, they're completely GOE. And the low energy field theory is a perturbed Luttinger liquid with precisely this vertex operator type correction. And in this case, the theoretical model predicts non-universal temperature scaling, which you can actually confirm with DMRG, as was done by Joel and collaborators. And the question we wanted to address was whether this has non-trivial consequences for heat transport near integrability. So naively, you would assume that the temperature dependence of the heat conductivity is given by Wiedemann-Franz scaling. Because the perturbation, the system is still in a metallic phase, you haven't perturbed it that strongly. I mean, it's hard to justify analytically or numerically, but many works which have studied this conclude that while the Lorentz ratio might be modified in the presence of interactions, the scaling seems to hold up. Unfortunately, it wasn't even possible to check it using DMRG because of the time scales at low temperatures. However, it does have non-trivial and testable consequences for transport. If this power law assumption is true, the energy density should satisfy an anomalous diffusion equation, or nonlinear diffusion, with exponents tunable in terms of the Luttinger parameter. And the fundamental solutions to this kind of equation are not the usual Gaussians. Instead, they're so-called Baron-Blatt-Patel profiles who have space-time scaling that depends continuously on this exponent. So to test this, we simulated XXZ in a staggered field with a localized thermal wave packet initial condition, as we also studied for GHD some years ago. And you can probe space-time scaling by looking at the logarithmic derivatives of moments of the wave packet. If you really have super diffusion, you would expect that all of these things actually converge to the same value at long times. So the non-trivial prediction of our model is then that these should converge to the same value, and this exponent should be between 2/3 and 1. And that comes from just thinking about how the conductivity needs to depend on temperature at low temperatures. And so for low bulk temperatures, we did find clear evidence for super diffusive rather than diffusive spreading of wave packets on the accessible timescale. You can see that the moments are for different moments, 2, 3, 4, 5, they're converging to the same value, but it's neither diffusive, which is the lower dashed line, or ballistic, which is the upper dashed line. Instead, it's an effective exponent of around 0.9. Unfortunately, the long-time scaling forms of the profiles is inconsistent with our simple model, which suggests that refinements are probably necessary to capture the detailed shape. There does seem, on the right-hand side of the plot, you can see there does seem to be some kind of scaling collapse, but it's not to the Baron-Blatt-Patel profile, which is monotonic on either side of 0. And so one thing we wondered whether proximate freedom of the Luttinger liquid or proximate integrability of XXZ was playing a role, and maybe there are slow modes in the system that we might want to take account of in some generalized hydrodynamic approach. But that's a direction for future work. And that's everything I wanted to say, and here are the associated papers, mostly preprints, but thank you.
Thank you. So, any questions?
Yeah, so going back to this first part of the talk,